So good day everyone, I am here to present the problems in 6.12. So problem 6.12, determine the maximum displacement of the cantilever beam caused by the concentrated load P. So given, cantilever beam fixed at A, concentrated load P applied at point B, distance from fixed end to load AB equals A. Total beam length AC equals L. The beam extends beyond the load to the free end C. So for a cantilever beam, the maximum displacement always occur at the free end C, so we need to determine deflection at x equals L. So using the elastic curve equation, EI d squared y all over dx squared equals m times the quantity of x. Since the load is located at x equals A, the bending moment x is only between A and B. For 0 less than or equal to x less than or equal to A, the internal moment is m times the quantity of x equals negative b times the quantity of A minus x. So for A is less than or equal to x less than or equal to L, there is no bending moment. So m times the quantity of x equals 0. Solve for slope and deflection in region 1. The differential equation becomes EI d squared y all over dx squared equals negative b times the quantity of A minus x. So once we integrate, EI dy all over dx equals negative b times the quantity of ax minus x squared all over 2 plus c1. So if we integrate again, EIy equals negative b times the quantity of ax squared all over 2 minus x cubed all over 6 plus c1x sub x plus c sub 2. So apply boundary conditions at the fixed end at A. So the deflection is 0, y equals 0 at x equals 0. So if we substitute 0 equals 0 plus c sub 2, thus c sub 2 equals 0. So the slope is 0 also. dy all over dx equals 0 at x equals 0. So if we substitute 0 equals 0 plus c sub 1, the c sub 1 equals 0. So the equations become, in the slope equation, EI dy all over dx equals negative b times the quantity of ax minus x squared all over 2. So if in the deflection equation, it equals to EIy equals negative b times the quantity of ax squared all over 2 minus x cubed all over 6. So find slope and deflection at point B. X equals A. So slope at B, EI delta sub B equals negative b times the quantity of A times the quantity of A minus A squared all over 2. So it will become EI delta B equals negative b times A squared all over 2. So delta B equals negative BA squared all over 2 EI. So the deflection at B, EI y sub B equals negative b times the quantity of A times A squared all over 2 minus A cubed all over 6. So it will become EI sub YB equals negative b times the quantity of 3A cubed minus A cubed all over 6. So it will become EI sub YB equals negative BA cubed all over 6. So EI sub YB equals negative BA cubed all over 3. So then YB equals negative BA cubed all over 3 EI. So determine deflection from B to C. From B to C, there is no bending moment, so the beam segment is straight. Thus, free end displacement equals YC equals YB plus delta B times the quantity of L minus A. If we substitute the values, it will become YC equals negative BA cubed all over 3 EI plus times the quantity of negative BA squared all over 2 EI times the quantity of L minus A. So if we factor out, YC equals negative BA squared all over EI times the quantity of A all over 3 plus L minus A all over 2. So if we simplify inside parentheses, 2A plus 3L minus 3A all over 6 equals 3L minus A all over 6. Thus, the maximum displacement equals PA squared times the quantity of 3L minus A all over 6 EI. So that will be all. Thank you.